All right, here we go. This is 2012, number 2. The last one that I'm going to do, I think, before the AP exam that has calculations in it, or at least calculations where you have to have a calculator. So here we go. This says a sample of pure gaseous hydrocarbon. So we have a hydrocarbon. We should anticipate that that's going to burn and produce carbon dioxide and water. It's introduced to an evacuated rigid 1 liter vessel. There's nothing else in it. 1 liter volume. The pressure of that gas in the vessel is 0.2 atmospheres, and they have a temperature of 127. Calculate the number of moles in the vessel. I've been guaranteeing PV equals nRT all along, and I can't guarantee that anymore. Mostly because they've kind of said that they're going to avoid calculations, and so we may not have PV equals nRT on the AP exam this year. That will be a first. At least in the last 10 years. So, and who knows, it may show up also. You should have a calculator handy next to you, just in case. So here we go, PV equals nRT. They gave us a pressure of the hydrocarbon, 0.2 atmospheres of pressure, times the volume. They gave us 1 liter. These guys both have 3 sig figs. Times N, because we're in atmospheres, we're using 0.0821. Liters times atmospheres over moles times Kelvin for our universal gas constant, and then we need our temperature in Kelvin, so it matches that unit. So we'll have atmospheres, liters, liters. Make sure that doesn't get stuck in there in milliliters. You'll be in trouble. And Kelvin's going to be 127 plus the 273 gives us 400 Kelvin, and we can solve for our moles of this mystery hydrocarbon. Which is going to be 6.09 times 10 to the -3rd moles, if my mental math's correct. Good. 3 sig figs on those things up here, 3 sig figs for the number of moles. You could put CXHY, we know it's some kind of hydrocarbon like that. If you put moles, that would be good enough there. And then we're to part B. That's it on part A. It says oxygen is introduced to the vessel. It's not a shock. So that hydrocarbon is going to burn. After the addition of oxygen, the pressure of the gas mixture in the vessel is 1.4 atmospheres. Calculate the partial pressure of the oxygen in that vessel. So we have a total pressure. This is like a really simple Dalton's law partial pressure problem here. Total pressure is going to equal the pressure of the hydrocarbon plus the pressure of the oxygen that was injected in there. They told us the total pressure after they put the oxygen in is 1.40 atmospheres. And we already know the pressure of the hydrocarbon, 0.2 atmospheres. And so the pressure of the oxygen there is just 1.2 atmospheres. That's so simple that you're so amped up that you can get confused on something like that and try to do some kind of crazy calculation. It's subtraction. That's all that's there on part B. Good? Alright, then it gets a little more fun. It says the mixture of the hydrocarbon and oxygen is sparked so that complete combustion reaction occurs, producing carbon dioxide and water. They shouldn't have to tell us that. The partial pressures of these gases at 127 are 0.6 atmospheres for carbon dioxide, 0.8 atmospheres for water. There is oxygen remaining in the container after the reaction is complete. Use the partial pressures of carbon dioxide and water to calculate the partial pressure of oxygen that's consumed. All right, when you can, start with an equation. So on part C, we get some kind of hydrocarbon, just means carbons and hydrogens, that are burning in oxygen. And when they do, we know they produce carbon dioxide and water, just like this. This is not a rice table, but I am going to show initials and final pressures here. Now this reaction happens to go all the way to completion, and so it is an equilibrium where all of these are going to react and go to the other side. And so I initially have 0.2 atmospheres of this, I have 1.2 atmospheres of that, and I initially have 0 of my carbon dioxide and water. That's what's initially in the flask. These guys react, and it tells me how much carbon dioxide and water are there at the end. After they react, the carbon dioxide is 0.6 atmospheres and the water is 0.8 atmospheres. So we go to 0.6 atmospheres here and 0.8 atmospheres here. Good? Which one of these is our limiting reactant on the reactant side? If we look here, it tells us there is oxygen remaining in the flask. So if oxygen is remaining in the flask, that's our excess reactant, which means this guy is going to go all the way to 0 because he's fully reacting. And so when we look at this, I've got to figure out, okay, how much oxygen do I have left? That's what they want, right? Use these pressures, calculate the pressure of oxygen consumed. So if I can figure out how much I got left, I'll know how much got consumed. So here's the deal. If 0.2 of this went away, then I gained 0.6 over here. What's the ratio of that? That means for every one of those I lost, I gained 3 of those. And for every one of these I lost, that 0.2 went away. How much of these did I gain? I got to 0.8, which means I gained 4 of those. Right? So my change was plus 3 times the x and plus 4 times the x to get those. And then I'm in great shape. Look at this. How many oxygens would be here? 6 plus 4 more there. That's 10 oxygens. Which means that should be a 5 in front of that oxygen there to give me 10 oxygens. Good? Good. And so for every one of these that reacted, 5 of these are going to react. And so how much do I have left of the oxygen? I have 0.2 atmospheres left. And so after the reaction takes place, .2 atmospheres of oxygen remain. They asked us how much was consumed. So 1 atmosphere of oxygen was consumed. That's our answer to that guy. That's part C. Good. Part D says, on the basis of your answers above, write the balance equation for the combustion reaction and determine the formula of the hydrocarbon. So here we go. We rewrite our equation, except now in part D we need to fill in what is the X and Y on the hydrocarbon. So how many carbons are here? 3 carbons there. That should be C3. There are 8 hydrogens there. That should be H8. That's my favorite compound in the world, propane. Because that's what I am. I think paine's a great motivator. We learn a lot in these struggles. And so here we go. So that gives us the 3, just like we thought. 3 carbons there, 4 waters there, and then we've got the 5 for the oxygen. There's our balanced equation in part D. Part E says calculate the mass of the hydrocarbon that was combusted. This is a weird question to stick all the way down at the bottom. The hydrocarbon here, right, we needed the X and Y to figure out what the molar mass is, but we know how many moles combusted, so we need to figure out now how many grams combusted. So we take the 6.09 times 10 to the negative 3rd moles. It's now C3H8. We know the formula for it, and we got to turn those moles into grams. 1 mole of propane equals 44 grams of propane. We multiply across the top and divide by the bottom, and we get 0.268 grams of propane. When in doubt, 3 significant figures. If you're not sure, stick with 3. And then the last one, part F, says as the vessel cools to room temperature, droplets of liquid water form on the inside walls of the container. Predict whether the pH of the water in the vessel is less than 7, equal to 7, or greater than 7. This is a highly missed question because it's easy to go pH of water. Water must be a pH of 7. Here's the problem. That water that's liquefying is in a environment with a huge amount of carbon dioxide floating around, and so when that water vapor and that carbon dioxide react with each other, that automatically produces some carbonic acid. And so some of that carbon dioxide is dissolved in that water, not a lot, but some of it's dissolved in that water. When it dissolves in that water, creates carbonic acid, and so we have a little bit of an acidic solution there. And if it's a acidic solution, then the pH will be less than 7. And you could put as the carbonic acid forms. That's a tough little point at the end with our carbonic acid, but that's happening in our bodies, right? As we breathe out carbon dioxide, it's mixing in with the water in our bodies, and it's making our blood a little bit acidic. That's why our pancreas has to secrete some sodium hydrogen carbonate, some more or less baking soda. That hydrogen carbonate ion helps to neutralize that acid to maintain our blood pH. That's a buffer problem. So there you go. That's 2012 number 2.